right. Hello, I'm Bill, and I'm going to be talking about higher order functions in Elixir and how they can make your code cleaner, more expressive, and also more maintainable. First, before I dive into some examples, a little bit about me. I'm currently working at the NAR company. We're a software consultancy in Boston. We specialize in web apps using a lot of technologies. Over the last couple of years, we've been diving more and more into the Elixir world. And as part of that, I've been working over at the MBTA, Boston's Transit Authority, kind of a surprising place to see Elixir. But we formed this little kind of entrepreneurish group that's trying to make customers' lives better with code without a lot of red tape. And all of our back-end stuff is done in Elixir these days, and it's been really, really cool and fun. So about me a little more, I come from more of a Ruby and object-oriented background. I've been dabbling in functional programming for a couple years. This is actually my first paying gig doing functional programming, which is really cool. And this talks a lot about some of the lessons I've learned in getting myself out of that mindset and making myself use functions in a better way. So start off with a little bit of review. What makes the functional programming functional? And there's probably some disagreement on this, but for me, immutable data, pure functions, and functions being first class. And that's what really applies most of this talk is using first-class functions to make things work better. And what is a first-class function? To me, three basic things. You can assign it to a variable, meaning you have some lambdas. You can pass functions to other functions as a parameter. And you can return functions from other functions, kind of the three main things. And if you're first diving into functional programming, that might seem a little bit weird. But in reality, I think everybody using modern languages, be it Python or Ruby or whatever, is using higher level functions all the time. They might not think of it as functional, but you're just doing it. Because you have things like map, filter, reduce, which implement an algorithm, and you pass in functions saying what to do with the data. And the common thing there between all these things that are using higher order functions is we're separating the algorithm from the data. We have a map algorithm, which takes a list, returns the same size list with transformations, a reduce, which filters it, or a reduce, or a filter. And they also all take that array, or that list they get, unwrap it, process it, and put it back together in some way. And as a result of all this, they're polymorphic. So we can take any of those functions and run it on any kind of data just by writing the correct functions that use that data. So with that in mind, I'm going to walk through a real-life example I did recently at the MBTA, kind of one of my first things I ever did professionally in Elixir, and talk through how I went from this naive approach that wasn't very functional, didn't feel great, to actually something that I felt really good about and felt really Elixir-y. So the problem looks like this. We had this stop on our T system, with this Wallison stop over on the right that is closed for 2 years. And it's like a really major inconvenience to our customers. People who are used to using that station can't use it for 2 years, have to be shuttle bussed around, and so forth. And the data store we use, or the actual back-end data form we use, is this industry standard. And when trains don't go through a certain stop, they just don't show up. And we draw our diagrams on the website using that data. So we were getting this thing on the left, and customers were like, what? Where'd this station that's been here for 50 years go? So there's no way to fix it back in that level, because the data format really prevents that. So we had to actually draw that back in place in the Phoenix program. So I'm going to walk through an example of how I did that. So super simplified version of data structure we're using, simplified much to fit on the screen. So a stop structure consists of a name and a flag saying whether it's closed or not. Pretty simple. And my first implementation, again, coming from that background, not using very functional stuff, looked a lot like this. And I'll walk through it a little bit to show you what the flow was. So first, that looks really weird. Sorry about that. So first we index into the list of stops we got, and first we index through and find the place we want to insert it. So we want to insert it after that stop. We look for it. Then we move on later. If that index does exist, we found this place we want to insert it. We, again, iterate through the list, find that stop before it that we want to clone. And then finally, we iterate through the list again and insert that new stop that we've just cloned. And that code works. It's not the worst thing in the world, but obviously it's kind of smelly, has some code smells. So let's walk through those code smells. First, it just feels iterative. It feels like I'm writing for loops in C or something. It doesn't feel like I'm doing something that's functional. And we saw in those last 3 slides, performance, we're doing 3 ON operations, so obviously not ideal. If we're doing a lot of data there, it's not going to be fast. And then finally, for me, it just didn't feel functional. It didn't feel like Elixir code to me. It felt like something I was taking methods I used in my old programming world and applying them to Elixir. So let's dive in and try to make this a little more functional. And my first attempt used something that was just out there, hanging out there, waiting for me, that I didn't think of at first, using flat map. So flat map is just like map, but you return in a list of elements instead of a single element. So you can make a list grow or shrink. You can shrink it by returning an empty list. You can grow it by returning a list with more than one element in it. It builds you a list of lists, and it conveniently flattens it at the end. And I used flat map and came up with this. So we have this high-level insert function. It takes a list of stops, the place I want to insert it, and the name of the new stop. I call flat map and pass it this one function process stop. And again, the process stop will take the stop, the place you want to insert it, and the name. And all I do is I look, am I processing the stop I want to insert after? If I do, I clone that new stop and return a list with 2 elements, the existing stop, the new stop. Otherwise, I return the stop in a list form. And that worked really, really well. The code was obviously cleaner. And my report card says it certainly feels a lot more functional. It feels like I'm writing Elixir code now. I've got 3x of performance. I've gotten rid of all those ON operations and replaced them with one flat map, which is ON. Still has kind of a conditional in it. Well, actually, not kind of. It really has a conditional in it. So I just went one step further on this one, broke this into 2 clauses, used pattern matching, and I've got 2 one-liners here, which to me is the ideal Elixir world. When you get these functions that look really clean, they're really expressive, they say what you want to do. So that was pretty awesome. That worked really well for me. I felt really good about how we were using Elixir. And then a second case came up. This one's a little more complicated. Here you'll see the missing Wollaston station. And this is a slightly different view, in that instead of showing one line, we're showing a more extensive view of our system where there's multiple branches. And this resulted in a data structure that looked more like this, where instead of just having that raw stop we had before, we have a tuple which has first element a list of all the branches that stop is on, and the second element of the tuple is just that stop we've already seen. So data structure is a little more complex. So implement it using the same method I did before, and you'll see it looks a lot the same. If you look at the code, it's kind of similar, but you'll see a little bit of logic where I'm using pattern matching in that process stop first clause to unwrap the stop and pull it out of that bigger data structure. And then down the line below that, you'll see I'm rewrapping that thing in a tuple and returning that. So again, code works, looks okay, but once again, our pig comes back and tells us we have some smelly stuff in this code. So what are the smells? First, it's not very dry. We have this algorithm, we're using multiple places, but we're implementing it completely twice. So if we have to go change something there, we're going to touch multiple places. Not always the ideal thing. So how do we go out and not implement an algorithm multiple times and find a way to reuse code? So when I do this, I like to look at the example and say, what's common about these 2 examples, and how can we use functions to clean things up and make things more reusable? So for me, the common things here were first we had to unwrap the stop. So we have that bigger data structure, in this case a tuple, we unwrap it, pull the stop out. Then later when we want to insert it, we have to take this bigger data structure, create that new stop, and plop it inside of that structure we already have. So it sounds like we have 2 functions there. So let's try to use some higher order functions to generalize this stuff and make these 2 things use common code. So first, let's make a new insert function. It looks a lot like the last one. We still pass in that list of stops, the place we want to insert it at, name of the new stop, but we've added 2 functions. One function that unwraps, one function that rewraps, and then we call flat map just like before, but the process stop again takes those 2 additional parameters, unwrap and rewrap. And we end up with something that looks like this. So it looks a lot like the code we saw before, and I'll just walk through how this works in comparison to the last one. So first, we unwrap. First thing we do when we get in here, we have a stop. This wrap stop is the bigger structure, and we unwrap it to pull that lower level stop structure out of there. If it's the place we want to insert it in this if statement, we just return, again, a 2-element list, the first being the stop we passed in, The second being this new stop we've cloned over here on the very right, wrapped again using this rewrap function. So the code is a lot like it used to look. Actually, I jumped ahead. We rewrap it, and we've got one function that does everything we did before, and we can reuse. So in order to see how this works, let's take those two examples we did previously, the stop and the branch view, and see if we can apply this function properly to make it work. So first case was that simple stop view where the stop was just that basic structure. In this case, the unwrap and rewrap functions are really trivial. In case the stop, we just return the stop, and the rewrap will return the stop as well, because that's just like the identity case. And when we call insert, we call it the exact same way, and it just works. So we check that one off. That worked really well. We're able to take that new function we wrote, which takes functions in, and reuse it. And now we'll dive into the slightly more complex example. Just a quick reminder, we're getting a structure that is a tuple there. It's the first element being a list of branches, second element being that stop we're familiar with. So how do we unwrap that? We basically just pull out the second element of the stop, of the higher level stop to pull that second one out. And to rewrap it, we just return a new tuple that has the existing element in that wrap stop along with the new stop we've passed in, which is our clone stop. And once again, we can use the exact same insert function to make this work. We just call it with the same parameters we did last time. We've just replaced those two unwrap and rewrap functions. So just summarizing that one, we use the same base code for both implementations. All we've had to do is make two simple functions that describe the differences between that. And as a side effect, we've now got something that's even easier to test, because we can test that algorithm separately just by passing in the simplest possible unwrap and rewrap functions to make sure the algorithm works. And to do something more complex, we just test those unwrap and rewrap functions separately. So we've got a lot of advantages there in terms of code being expressive, code being more dry, and easier to test. So that was all cool. And as always happens in the world we live in, there was a third example that came up we didn't know about. We had this third area where we were doing something more complex. We're drawing the lines on our website, but we're also adding schedule information. So we want to be able to tell the users where the predicted or actual times are going to be for any train at any stop. And once again, a really overly simplified version of the data structure for this. We have this new structure called schedule stop, which has about 100 other things in it, but we won't care about that. But the key things it has both a predicted time and a scheduled time for every stop. And that there can be nils involved here, because we could have a train that has a predicted time but no schedule, a train that's been inserted at the last minute as not on the normal schedule. We can have ones that are scheduled but not predicted. It hasn't started its run yet, so it's got a scheduled time in there but no prediction, or it can have both. And we see all those cases and have to handle them all. So let's dive in and try to write the unwrap and rewrap functions, see if we can use the same code for this new implementation. And again, very simplified version of what we're doing here, and it's pretty straightforward. We want to just be able to handle all these cases. If we are working with one that has a prediction but no schedule, we want to use the prediction because that's the thing that's what the users want to see, so we pull out the prediction. Second line, if we have just a scheduled but no prediction, we want to use the stop that comes out of the scheduled structure. And if we have both, we choose the prediction over the schedule because we want to show that times we know are more accurate versus the scheduled ones. And so that gives us our unwrap function. To rewrap things, it's a fairly similar thing. We're just doing a deep insert back into this nested set of structures here. So we take the scheduled stop we got, and we take that new clone stop we have, and we stuff that both in the predicted area and the scheduled area. And magically, we can call the exact same insert function at the end, passing the same parameters with these two new functions, and we've made this other part of our website work with no code reuse, with lots of code reuse. So here, the Refactor report card here is that we really had to do no refactor. We did the work on those first two implementations, and it all just worked. And we just had to implement those two new functions, those unwrap and rewrap. We had to understand the data structures involved, build those two functions, and it worked. We had to just test those two small functions. We trusted that the algorithm we were basing on the insert function worked already, and we were done. So we were able to really make our world a lot better by not having all this repeated code. And just diving in a little more and talking about what lessons we learned at a higher level here. My big lesson, somebody from like me coming from more of an object-oriented background into Elixir or functional programming for the first time, take your time to learn the Elixir Renew module. There's so much good stuff out there, and you can save yourself a lot of trouble in rewriting the world just by learning that and understanding how people apply the various functions there. Me not really thinking about flat map in the correct way set me on that other path first on. And second, be really, really relentless about drying up your code. If you find code that's repeated, think about what's common between those two areas you're repeating the code in, and where can you maybe use a higher level order function to encapsulate some of that knowledge there so you can have the algorithm separate from the data. And then finally, trust your sense of code smell. If something, you're looking at it and it doesn't look like what you expect Elixir code to look like, or if it doesn't feel functional, or it feels like you're writing C code in Elixir, there's probably a smell there. And in many cases, that smell can be fixed by just using higher order functions to abstract what you want and make it work. And the last one is kind of a summary of all this. Find ways to separate your algorithms from your data types so you can reuse what you have and separate that stuff. So that's kind of the bulk of what I wanted to talk about, my lessons learned there. And finally, some thank yous. Thank you to EMPEX for letting me do this. It's been a really well-organized conference. I had to do no thinking as part of coming here, except for my talk, and I love that, so thank you very much. Thanks to everyone at the MBTA. Again, I jumped in not really knowing Elixir super well in this job, and had some great code reviews from everybody, especially Paul Schwartz, who was my code review guru who tore my code to pieces, and in the process taught me a lot of stuff. Really appreciate that. The NAR company, my company, for allowing me just to have a job where I can write Elixir code. That's like the coolest thing in the world. And then finally, Farm Sanctuary in Watkins Glen, New York, actually wrote my talk there sitting on a cabin porch, and kindly the pigs at Farm Sanctuary volunteered to be one of my slides for this thing. And it was just an awesome place to work. They're an awesome organization, and really great to be able to be there and write a talk while sitting on a porch in a farm field. And finally, if you want to contact me in any way, you can reach me on Twitter. I'll have the slides up pretty soon on my GitHub. And if you have any questions or want to talk about anything, feel free to find me after the talk, and I'll be glad to talk to you. Otherwise, enjoy the rest of your conference and have a great day.